In the last video, we proved that the law of sines holds true for acute triangles and right triangles. And in this case, we're going to be looking at this third case where the triangle is obtuse. We're going to take a similar approach that we did for the acute triangle in that we are going to draw some altitudes into this particular triangle. So the first altitude I want to draw is the one from point C to the opposite side AB, and we'll call that H sub 1. So remember, what we're doing here is we're trying to, within this triangle that is not right, create right triangles. Now this point where the altitude meets segment AB, we're going to refer to that as point D. So we now have two right triangles that we can talk about, triangle ADC and triangle BDC. And as I said, we're going to refer to this height as H sub 1. Okay, so with that in mind, we're going to look at triangle CBD first. And in that triangle, we want to set up a sine function for angle B. So the sine of angle B would be the length of the opposite side over the hypotenuse. So the opposite side is going to be H sub 1. The hypotenuse in that triangle is A. Multiply both sides by A, and that gives us a quantity that is equal to H sub 1. Now let's consider the other right triangle that we have, in this case triangle ADC. In triangle ADC, we have acute angle A. So let's look at the sine of angle A in that triangle. The sine then represents the opposite side H sub 1 over the length of the hypotenuse, which here is going to be that lowercase b. We want to multiply both sides by b, as we've done similarly in other exercises, and that isolates H sub 1. Now, as we have done previously, since these two expressions are now equal to H sub 1, they have to be equal to each other. So A times the sine of angle B is equal to B times the sine of angle A. And then, as we did in the previous video, we're going to divide both sides by the product AB. And there again, we know these are non-zero numbers because they are side lengths in this triangle. So the A's here are going to cancel, and in this case the B's, which leaves us with the sine of angle B over its opposite side B is equal to the sine of angle A over its opposite side A. So that part is very similar to what we did with the acute triangle. Now, in the case of the acute triangle, what we ended up with when we drew our second height, it was also inside the triangle, which led us down a very familiar, similar path to this one. The problem with an obtuse triangle is that another altitude, since the triangle is obtuse, the other two altitudes both lie outside the triangle. And in this case, I want to look at the altitude that would go from point A perpendicular to side CB. Now, in order for that to happen, I'm going to have to start by extending this segment CB. We'll do that with just a little dash segment outside the triangle, leaving everything in the original diagram as solid lines, something like so. So if we extend segment CB, then our diagram becomes this. And now it's possible to draw a segment from point A perpendicular to that side CB. In which case we end up with something like, get everything set up well here, something like so. And I'm going to call the point where these meet, we'll call that E. And I want to refer to this altitude that we just drew here, we're going to call that H sub 2. Okay, so now we still have two right triangles that are in place. The two right triangles that we have here would be the right triangle BEA and the right triangle CEA. Now you may be kind of hesitant here to use triangle CEA because it lies outside the original triangle. And when we talk about angle C here in the law of sines, we're referring to this angle ACB, that obtuse angle that we started with. But there is some relationship that's going to hold true. It's going to pop in just a bit. But for now, let's look at that triangle BEA. In that right triangle BEA, angle B that is an angle in that triangle is also the same angle B that we're referring to here and that we looked at in this case. So with this angle B, we know the sine of angle B is equal to the leg opposite the angle, which is at h sub 2, over the length of the hypotenuse. Now in this triangle BEA, side AB, which we said was C units long, is the hypotenuse. So just as we've done before, we'll multiply both sides by C, and that's going to isolate then that h sub 2. Now let's consider triangle CEA. We're trying to come up with something that's going to involve this sine of angle ACB. But in order to do that, since ACB is not in this triangle, let's look at its supplement, which is here, angle ACE. So the sine of angle ACE would be the opposite side to h sub 2 over the hypotenuse, which in this case is B. So B times the sine of angle ACE is h sub 2. Okay, so to progress forward, we need some way to incorporate angle C. Now remember, this angle C in our law of sines, this is angle ACB in our triangle. It's that original obtuse angle. So let's consider what happens with angle ACE and its supplement, angle ACB. What happens when you take the sine of an angle or the sine of its supplement? So if we consider the sine of 30 degrees, which is a half, and the sine of 150 degrees, which is also a half, we can see that they're equal. We could look at other examples. The sine of 60 degrees is root 3 over 2. The sine of 120 degrees is still root 3 over 2. It can be easily shown that the sine of an angle and the sine of its supplement are equal to each other. So for that reason, since the sine of angle ACE is equal to the sine of its supplement, we can replace this sine of angle ACE with the sine of its supplement, angle ACB. Now to understand that, you have to fully understand how sines of supplements work. If you're struggling with that, then that's something you'll need to research or contact someone about a little further. Okay, so we've now got two quantities, both of which are equal to h sub 2, so we can set those equal to each other. And from this point, this proof is going to be very similar in structure to what we've done both in the acute triangle and what we did up here in the red. Okay, so we're going to multiply, or divide rather. We're going to divide on both sides by the product of these two side lengths BC. And there again, neither B or C is 0, so we don't have a product of 0. And divide by, or cancel out our C's, cancel out our B's, and we're left with the sine of angle B over B is equal to the sine of angle ACB. Remember, that's what in our original triangle, that is simply angle C in our original triangle. So what we've now shown is that this sine of angle B over B is equal to both the sine of angle A over A and the sine of angle C, if we simplify it, over C. So there again, we can see that the law of sines holds true if the triangle is obtuse. So we've now proven that it works for the acute triangle case, the right triangle case, and case 3, the case of the obtuse triangle. And that completes our proofs of the law of sines.